go through, and we just want to say thank you and appreciate everyone that came up tonight. Okay. So tonight we're debuting a brand new design for an ultrasonic meter tube, including upstream and downstream end treatments. So with that, because we've got a mixed crowd tonight, some of this will be elementary to some of you, but for the others, just so that we're all able to get on to the same page. I'm going to show a couple of pictures. This is just representative from an industry standpoint, different examples of current end treatment designs. And for those of you that do work for multiple different end users, you'll probably recognize the geometric shape of some of these end treatments. I don't have any of them labeled on purpose, but you'll probably be able to pick out who they are. So you can see a different design there. And really industry-wide, there's a different design for end treatment almost for every end user. So there's 3 different designs that are used for end treatments, okay? So I'm using this word end treatment. First, let me just describe what end treatments are and why they exist. For a lot of the folks that are here who are involved in measurement, the measurement supervisors don't necessarily have jurisdiction regarding the geometry of the piping that's coming into the measurement station. So what happens is, as we understand in our world, there are tons of installation effects that can wreak havoc on a meter. And if you don't have jurisdiction on whether it's 3 elbows in plane, out of plane, 2 elbows, whatnot, all you have is jurisdiction over this square footprint, then what happens is each end user takes it upon themselves to come up with an end treatment design. So the upstream end treatment design here, the idea behind it is so that no matter whatever crap is coming into the measurement station in terms of turbulence and flow profile, we are going to run it through a specific piping geometry in an effort to get a repeatable profile when it comes into the meter. That's the purpose of this upstream end treatment. It's all about getting the same profile every time that it comes into the meter, and every end user goes about it a little bit different. Now the downstream side, even though it looks the same, is actually for a completely different reason. After the measurement station comes the regulator station, so there are control valves, and these control valves, when they're regulating pressure, they generate a lot of noise. Not just audible noise, they generate a lot of ultrasonic noise. And what happens is that ultrasonic noise makes its way back to the ultrasonic meter. The ultrasonic meter has a hard time distinguishing between the transducer signal in the meter and the noise being generated by the control valve. Very much like if you're driving between Austin and San Antonio, and you've got your radio dialed to 98.9, and it's Air 1 in Austin and it's Kiss FM in San Antonio, you eventually hit that spot where your receiver doesn't know which one to listen to, and that's because the strength of the signals become equal and it has a hard time figuring out. That's what happens to an ultrasonic meter when the noise gets too loud and it starts to overcome that transducer signal. So for that reason, there's a downstream end treatment whose purpose in life is to attenuate that ultrasonic sound. But as you can see, it takes up a lot of space in order to accommodate these 2 end treatments. In the process of developing M3, which we released a little over 2 years ago, we made a great discovery. The discovery was, because we were trying to build a mobile platform that would be compact, we were looking for the most compact upstream end treatment that could regulate that flow profile and give us the repeatability we were looking for. We found, as I present when I do the M3 presentation, that when we use the 2 flow conditioner arrangement of the 50E and the 55E, that it perfectly removed the swirl generated by 2 90-degree turns in plane. The reality is that we ran it through multiple scenarios, not just 2 90s in plane, but we actually could not throw a scenario at it where it really disrupted the flow profile to anything that we could distinguish. So we learned that the upstream side of the tube really didn't need this sweeping end treatment in order to get a repeatable profile at the meter. And this got our cranks turning, because and I've got a couple other fabricator companies here, which I really appreciate you all coming. So we all experience this. We build these systems for a lot of our different clients, and so we get to see all these different varieties of end treatments. Well, because of what we discovered on M3, it got our cranks turning, thinking, you know what? Like, we now have an upstream end treatment that never leaves the center line of the meter. Can you imagine what the skid would look like if we were able to come up with a solution on the downstream side that also never left the center line of the meter? So we began So we began our quest to find something on the downstream side that would attenuate ultrasonic noise but never leave the center line of the meter. And so we're calling it the Big Elk Ultrasonic Sound Attenuator because we haven't come up with a better name yet. Just to give you an idea of footprint comparison, this is our inline meter design. This is another end user standard end treatment design that you'll probably recognize. We affectionately call it the H pattern. Our design is a 64% smaller footprint than this design. You may recognize this design. It's an elbow into a attenuating tee. Our footprint is 74% smaller than this standard industry design footprint. Okay, so here's what we do in order to accomplish this downstream end treatment that's going to attenuate ultrasonic sound without leaving the center line of the meter. The idea was that as we're coming out of the meter, say it's an 8-inch meter tube, we're going to go into an expanded pipe section, so say into a 12-inch expanded pipe section. And we're going to weld in baffles so that the ultrasonic sound cannot make its way back to the meter, but likewise, because it's a 12-inch pipe section, even with the baffles, which would represent typically some form of restriction, we have it designed so that the cross-sectional area, it never changes from the 8-inch full-bore pipe. So if you look at it from the natural gas perspective, if you're the gas flowing through the meter, once you flow through the meter, you never really know that you've left an 8-inch pipe because the cross-section area never changes. So now you go through this attenuator piece, and now any ultrasonic noise generated by a control valve can't make its way back to the meter. And this, our friends at CPA also helped us put this CFD together just to show the CFD of the attenuator itself. Of course, we have a 3D model that everyone can come and look at, pick up and hold, and probably break, and that's okay if that happens. Okay, so now for the lab test, just to show you whether or not this thing actually works. So we ran 3 tests. One was a baseline where we used a swirl generator developed by our good friend Dennis, which was basically 3 90s and 2 45s all out of plane. And it wreaked havoc on the system. And that was followed by a standard AGA 92, 10D, 50E meter. We only had 7D on the other side, or excuse me, we had 7D instead of 5D. And then a control valve that was going to be generating the ultrasonic noise. Then we had our design, which was the swirl generator, followed by the 2 flow conditioner arrangement, the meter, and then our noise attenuator downstream. And then we had what I'm calling an industry standard end treatment, which is just a typical end treatment used by a typical transmission client. So we had the swirl generator, then followed by their upstream end treatment, the AGA 9 tube, and their downstream end treatment. We ran a bunch of test scenarios, but rather than just bombard you with data, I'm going to go right to the one that was the most meaningful, which was the most dramatic one. 400 pounds of differential at 80 feet per second, and that's with the control valve that's creating all of this ultrasonic noise close coupled to the downstream spool. So it had direct line of sight to the meter and the baseline, and then went through our attenuator for the other scenarios. Okay? So on this first chart, this first flow simply shows what it would look like when there's no disturbance, right? So there's no turbulence, nothing at all. That would be the ideal line that you would like to achieve. This line here at the bottom is when there was no end treatment at all. So as you can see, the signal to noise ratio, it got very low. I don't want to say that it broke the meter, but the meter was certainly having to work incredibly hard to try to continue communicating. The industry standard end treatment is this line here. So as you can see, there was a considerable improvement over having no end treatments at all. Our goal when we set out on this was really just to meet the performance of an industry standard end treatment. Because keep in mind, as long as we can perform as well as an industry standard end treatment, our win is that we take up a lot less space and cost less money. The reality is when we tested the design, it performed much better than the industry standard end treatment, because this is that scenario at 80 feet per second with 400 pounds of drop. We barely got below 32, 33 on the signal to noise ratio. Likewise, when it comes to the upstream side performance using the dual flow conditioner arrangement versus the industry standard end treatment, again, when you look at the symmetry, you can see a clear winner. The first flow would be your ideal. Obviously, 1 is kind of your ideal scenario from a symmetry standpoint. and you can see that this was the industry standard in treatment here, and here's the dual flow conditioner arrangement. The Big Elk Inline system is here, and it started at 1.01 and ends at 1. This is just a picture of the installation. So this was the baseline where we had the swirl generator into just a straight AGA9 tube. This is the swirl generator into an industry standard in treatment, upstream and downstream. And this is the swirl generator into the Big Elk Inline system, and this is a second picture of that. And this is a picture of the Inline Attenuator itself. So as we concluded the data, what we're excited just beyond belief to roll out, it's very real. We think it's an absolute game changer, which is we're releasing our design for a complete ultrasonic meter tube. It costs less, it takes up dramatically less footprint, and it's higher performing than any other industry standard in treatment. So we've got a PO form at the door.
Sign me up!
For questions, you can come see the 3D model, and then anyone who'd like to get over to the Emerson, please feel free. We'll be around for another hour or so. Drink to your heart's content. And again, thank you everybody for coming.